So good afternoon to all. Sorry, good morning. Are you alert?
Good morning, sir.
Good
Yes,
morning.
sir.
Good morning. It's not good afternoon. Okay. So let's start. Let me share my screen. Okay. We start writing. After that, I'll go down. While writing epsilon and epsilon dot, you be careful. There are two terms. One is epsilon, another is epsilon dot. Epsilon dot is nothing but your strain rate. That is, if you do d epsilon by dt, that is actually symbolically mean by sigma epsilon, sorry, epsilon dot. Okay, I can show you here. So epsilon dot is nothing but your d epsilon by dt, rate of change of strain. So is it done? Can I go down? Can I scroll it down?
Wait, sir. I will finish.
Sir, we cannot see full part of your screen, sir.
Full part I will have to go up. Then only you will get see. Means
No,
what I
that
will
side part,
do.
like
Part.
how?
This is
Yes, side,
now.
like on. No, sir. We can like on the other hand, then we cannot see on that,
There is nothing is. There
like
is nothing. Only comma is
like
there.
and for
For
that
elastic
both
material.
stress or yes, sir.
For viscoelastic material, there is nothing actually. This is the boundary.
Yeah, now we can see.
See, this is your boundary. This is your boundary. And this side also, this is your boundary. Is it okay now?
It's clear now. Now
Ah.
it's now we are seeing all the ports.
Hmm. You write quick.
Okay, sir, done.
Done? Is it done or not?
Yes, sir. Done.
Okay, if it is done, let me explain a bit. Is it done?
Yes, sir.
Okay, now let me go up.
Yes, sir.
So, so what is linearly viscoelastic materials? Okay, so you have come to know different type of material, solid material, okay, some amorphous, crystalline, those type of things, right? Amorphous materials are your glass, crystalline materials are your metals, okay. So what happened actually? Hooke's law is valid up to elastic region. That means sigma is proportional to epsilon. Strain is proportional to stress. Okay. So those material which obey Hooke's law are called your elastic materials. But what happens? These elastic materials, after certain period of time, maybe 50 years, maybe 100 years, or sometime it may be even 1 month, 30 days. Okay, the same material which was elastic earlier changes its property to viscous material. Why? Due to the continuous stress applied on that particular material. So that thing happens. And in that case, you will see stress is no longer proportional to strain, but one additional term that comes, which we call as strain rate, and that strain rate is directly proportional to stress, provided you have used your coefficient of viscosity. That means you know what is viscous material, like your honey that you eat, honey. So honey is a viscous material. You know what is the profile of viscous material. You will come to know in your fluid dynamics, fluid mechanics. Okay, in your fluid mechanics, you will see that viscoelastic materials are some of the examples. Then, what is the governing equation for viscous material? So, viscous material example is your honey. Okay, so these materials, solid materials, also due to overloading or due to continuous loading over the period of time, it loses its property and convert or transform into viscoelastic material. The details of this I am not going into it because it is related to your material science. Phase change occurs. Okay, so such kind of phenomena. If I want to give you an example, why this thing happened by what phenomenon? One phenomenon is called creep. So creep is a phenomena. If you keep something under load, let it be small load, but you keep it for 100 years, then you will see that the material after 100 years it develops a permanent deformation into it. Okay, not necessarily your load should be very high, it may be low, but you have to keep it for a long time. So creep is a time dependent phenomenon actually. Okay, this happens normally in the pipelines through which this nuclear energy are passes, no, and maybe in your pipeline like crude oil, petrol, those type of things in this pipe also these creep things happen, and because of that the material gets failed. So linearly viscoelastic materials, the governing equation is yours, not sigma is equal to Young's modulus into epsilon plus your coefficient of viscosity into strain rate. So strain rate is nothing but your strain rate that we denote by sigma dot, sorry, epsilon dot, and that is nothing but is change in rate of change of strain. Okay, so this is viscoelastic material. Then come to cyclic loading or fatigue. Okay, so in manufacturing process or workshop technology, such kind of subject. Have you gone through it? Any subject of any of these subject, manufacturing process, workshop related subject? Have you studied in your early semester? Okay, let me tell you. So cyclic loading is something which is the load is a continuous process in a cycle. Okay, one after another. So what happens in cyclic loading? The material property, similarly in the other case also, the material property loses when you put it cyclically. For example, you take the suppose a motor. You can take the example of a shaft which is rotating in an automobile. Okay, so these type of materials are undergone fatigue, and that kind of fatigue is due to your cyclic loading. So fatigue is primarily related to your cyclic loading, but sometimes some materials fail even if very after going through a very few number of cycles. So those materials we can call low cycle fatigue, and if it's so many millions of high cycles, then we call it high cycle fatigue. Okay, so fatigue is also happens to human being also. Sometimes we get fatigue due to overload. Okay, so similarly in material also fatigue occurs, which is due to cyclic loading. Cyclic loading, remember this term, cyclic loading, not any other loading. Okay, are you clear? Are you clear?
Yes, sir.
Okay, then let me deduce the expression for elastic strain energy for initial stress. What happens? What is happening? Many time I have seen this thing. Initial. We are considering this phase. So if you do like this is y, this is z. Now you draw another figure. We are considering one dimension. These are all straight line. These are not curves. These are all strain energy. Areas are forces and deflection deformations are and deformations. Would you follow me? Those are distances. The product of this two quantities, product of these two quantities is the internal work done. Internal work done in a body through applied process. This internal work is internal work stored stored in an elastic body with the internal elastic body. Of the position of the elastic stimulation. So that nine decimal will be subjected to to a normal stress element. Somebody please take the attendance. Subjected to Bhagirat, you take the attendance and send it to me. No one subjected to a normal stress element. Right. Right or left face. Right or left face. This element is sigma x divided by z. Where dy dz is an dimensional area of the element. Figure out? You took the attendance because at any time this meeting may be closed. Okay, you take because of this force. The elements elongates in the element elongates and mount sigma x dx, where sigma x is normal strain in the x direction. If the material is made of if the material is made of linearly elastic material, linearly material stress is proportional to strain. Proportional to strain as shown in figure. Therefore, if the element is if the element is if the if initially free to stress, initially free to stress, the force that finally act on the finally act on the element increases linearly to zero 0 until it attains its full value. So what is force acting in the this force acting in the element of the formation is taking place is place place is a sigma x dy dz. This reference force multiplied by distance to which the distance for which x is the total element of element for a perfectly elastic body. For a perfectly elastic body, no energy is dissipated. Energy is dissipated when the open element is greater than the. Are you able to follow, right? So, you have any problem writing? Yes, recoverable. Strain energy. Rather than elastic energy. Dance. Are you able to follow? Yes. Internal elastic strain energy. Hello, nobody is responding.
Yes, sir.
Sometimes he responds. This is infinitesimal. One, so the three stress. Subject to MGL stage is du is equal to half sigma dy dz into this is your average force, and this part is your distance. So force into distance, we know that is force into its distance. So total will be your work. Okay, so equal to half into sigma x into epsilon x dx dy dz is equal to half into sigma x epsilon x. So dx dy dz nothing but is your volume. So that we write as dv. Put equation number 1. When by recasting equation 1, the strain energy stored strain energy stored when elastic per unit volume volume. So it will get over in another 5 minutes. Volume, the material, volume of the material or its strain energy or its strain energy density. Density U naught is obtained thus U naught is equal to du by dv is equal to sigma x epsilon x by put equation number 2. This expression may be basically interpreted as an area near the inclined line in the statistic diagram, and the stress strain diagram as shown above. Equation 2 can be derived for order to mutually perpendicular directions. Since in elastic range region Hooke's law is applicable Gauss law is that is sigma is proportional to E into epsilon. Therefore, equation 2 gives U naught is equal to du by dv, okay, equal to sigma x square by 2e. Put equation number 3, or u is equal to, this is volume integral, or you can put three integral signs. Okay, so let us stop here. So another two things were there, so I'll give you in the next class.